Hey, welcome to The Explainer. Today we're going to break down the fundamentals of software architecture. So if you've got a competency exam coming up, you're going to want to stick around. This is for you.
Well, it all comes down to scale, right? And complexity. And of course, design. I mean, a simple script does one thing. But a system like Netflix, it's juggling millions of problems for millions of people all at the same time. And the thing that makes that possible, that's architecture.
So here's the best way to think about it. You wouldn't even think about building a skyscraper without a super detailed blueprint, would you? Of course not. And it's the exact same idea for software. The architecture is that blueprint. It lays out all the big pieces, shows how they're all going to connect, and sets the rules for how the whole thing gets built.
All right, so here's our game plan for today. We'll start with the basics, the what and why. Then we'll get into the actual building blocks. After that, we'll talk about the tough decisions, qualities, and trade-offs. We'll check out some common designs you'll see out there, and we'll wrap up by getting into the mindset of an architect.
Okay, let's jump right in. We've been throwing around this word blueprint, but what does it actually do? What's its job?
Well, that blueprint is all about making sure the thing we build actually works the way it's supposed to. That it has the right qualities. Like, can it handle a ton more users all of a sudden? That's scalability. Is it going to be a nightmare to fix or update later? That's maintainability. Does it, crash all the time? That's reliability. A good architecture is what makes all of this possible. It's the foundation for success or failure. Okay, so if the architecture is our blueprint, what are we actually building with? What are the bricks and mortar? Well, in software, the answer is modules. These are the little self-contained chunks of code. Think of them as the building blocks that make up the whole system.
All right, check this out. On the left, you've got what we call spaghetti code. And yeah, it's exactly what it sounds like, a total tangled mess. Everything's connected to everything else. You change one tiny thing over here, and bam, you break something way over there. But on the right, that's modular code. It's organized, it's clean, the functions can be reused. It just makes sense, way easier to work with.
So, how can we tell if one of our building blocks, our modules, is actually any good? Well, the first thing we look at is cohesion. High cohesion is a good thing. It basically means a module has one job and one job only. Think about it. A module that handles customer profiles should only deal with customer profiles, not their orders, not their shipping info, just profiles. It has one well-defined purpose.
And the other side of that coin is coupling. Coupling is all about how tangled up your modules are with each other. And here we want the opposite of cohesion. We want low coupling. This means our building blocks are nice and independent. You can swap one out or change it without causing this massive domino effect across the entire system. So remember this, because it's key for your exam. High cohesion, low coupling. That's the mantra.
Okay, now this is pretty cool. You might think this cohesion thing is just a vague idea, but we can actually measure it with a number. This table breaks down a metric called LCOM, which stands for lack of cohesion in methods. Sounds complicated, but stick with me, it's not that bad. So here's how it works. First, you look at every possible pair of methods in your module. Then you just ask a simple question for each pair. Do they use any of the same data, like the same variable? All the pairs that don't share data, we'll call that group P, and the ones that do, we'll call Q. So in our example here, you can see we found 5 pairs that are totally independent, so P equals 5. And only one pair, the set salary and calculate bonus one, actually shares some data, so Q equals 1. The formula is super simple, it's just P minus Q as long as P is bigger than Q. So for us, that's 5 minus 1, which gives us an LCOM of 4. Now a high number here is actually a bad thing. It's a big red flag that says, hey, this module has low cohesion. It's probably trying to do too many different things at once, and you should really think about splitting it up.
And that decision, whether or not to split up a module, that's not just some small technical choice. It affects the whole system. Which brings us to our next big topic, the quality standards the entire architecture has to meet. You'll often hear these called the abilities.
These are the big picture qualities. It's not about what the system does, it's about how well it does it. Is it fast? That's performance. Can it be trusted to stay online? That's reliability. Is it safe from hackers? Security. You get the idea. These are the questions an architect is always asking.
Let's make this real for a second. Take reliability. This isn't just some abstract concept. Sometimes it's literally life and death. Think about an air traffic control system. Failure is just not an option, right? So the architecture is designed with tons of redundancy. If one piece fails, a backup kicks in instantly. A single point of failure just can't bring the system down. That is reliability by design.
Or how about scalability? This is something you see every day. Imagine a post on a social media app suddenly goes viral. The traffic can jump by 1,000% in just a few minutes. A bad architecture would just crash and burn, but a scalable one? It automatically grabs more resources from the cloud to handle that massive load. And then, just as important, it scales back down when things quiet down. It breathes with the demand.
So this leads to a really fascinating idea, captured in this quote. See, the goal isn't to build the perfect architecture, because that doesn't exist. The real goal is to find the one with the fewest, most acceptable downsides, the least worst option.
And this brings us to what is basically the first law of software architecture. If you remember one thing from today, make it this. Everything is a trade-off. It's a constant balancing act. If you crank up security with a bunch of extra encryption, guess what? Your performance is almost definitely going to take a hit. If you build for maximum internet scale scalability, you're probably giving up some simplicity. Every single decision is a compromise. Okay, so knowing you have to make trade-offs is one thing. But how do you make them? Well, architects don't start from scratch every time. They use proven designs, or architecture styles. Think of them like pre-approved building designs that already come with a list of pros and cons.
A super common one, maybe the most common starting point, is the layered architecture. You see this a lot inside what we call a monolith, where the entire application is just one big, single unit. It's pretty straightforward, right? You've got a layer for the user interface, a layer for the business rules, and a layer for the data. Because it's simple to get started with, you see it everywhere.
Okay, so that looks pretty neat, right? Everything in its own little box. But there's always a catch, isn't there? What do you think the downside is? Well, as these systems get bigger and bigger, that monolithic style can become a real problem. Everything gets tangled together. You want to make a tiny change in one little spot? Suddenly you have to test and redeploy the entire application. It can really slow you down. So what's the trade-off here?
And here's a perfect example of that trade-off in action. It's called the sinkhole anti-pattern. An anti-pattern is basically a common solution that looks good on the surface, but ends up causing more problems than it solves. In this case, just to keep the layers pure, a simple request might get passed from the top layer to the bottom layer through a middle layer that does literally nothing with it. It's just wasted work, slowing things down. So to get around this and other issues with the monolith, architects came up with different styles. You've probably heard of microservices, right? That's where you break the app into a bunch of tiny, independent services that talk to each other. It's great for scalability and letting teams work on their own, but man, it can be way more complex to manage. Or there's event-driven architecture, where different parts of the system just react to events happening. That gives you incredible flexibility, but it can also make it really hard to follow what's going on. See? Every style is just a different bundle of trade-offs.
All right, last section. Let's bring this all home. Because being an architect isn't just about knowing a bunch of patterns from a book. It's about a completely different way of thinking. It's about making that jump from developer to architect.
A developer's knowledge is often V-shaped. They go deep, they become an expert in how to build something amazing with a particular technology. An architect, on the other hand, needs an inverted V. Their knowledge is broad. They need to know enough about lots of different technologies and patterns to understand why you choose one over another for a specific problem, always thinking about those trade-offs. It's really the difference between being a master craftsman who can build a perfect staircase and being the person who designs the entire house and decides where the staircase should even go.
And that really brings us back to the core idea and the final question I want to leave you with. Remember that first law, everything is a trade-off. So for your next project, the most important question isn't just what features will we build? The real architectural question is, what are we willing to sacrifice? Are you going to give up a little speed for rock-solid security? Are you going to take on the complexity of microservices to get that massive scalability? Just understanding and accepting that you can't have it all. Well, that's the first real step to thinking like an architect.